Hey guys, welcome back. In section 12.3, we're going to take a look at how pressure varies with depth. Now, this picture shows a person swimming underwater, but you could be in any kind of fluid, not just water. And in physics, fluids mean liquids and gases. And so, technically, everything that we say in this section would apply equally to being in the Earth's atmosphere, for example. It would apply to dropping a probe into Jupiter's atmosphere, whereas the probe descends through those thick, thick clouds. The pressure increases and increases and increases. So please don't let the picture fool you. Everything in this section applies to gases as well as liquids. And the thing to take away, I guess, is that, and this is getting a little bit ahead of ourselves, but you'll notice that the arrows on top of the swimmer are shorter while the arrows on the bottom of the swimmer are a little bit longer. The idea there is that anytime you put something into water, you're going to get a little bit of buoyancy. And that buoyancy is related to the fact that there's just slightly more pressure underneath the object than there is above the object, right? You'll also notice that these arrows are pointing in basically every direction. And that's because pressure is exerted in every direction. We're used to seeing arrows with vectors like force or velocity. But with pressure, we see the arrows, but pressure is certainly not a vector. Pressure is exerted against every surface, against every possible direction that the surface allows. So let's jump into it just a little bit. What this picture is showing, and I guess I should say there's a derivation that goes along with this, and the focus of this class isn't really meant to be mathematical, but if for some reason you really wanted to see the derivation, you could go back and click on this OpenStax textbook. In fact, I can even provide a link in Classroom if you'd like that. But if you click on this and you go to the section on variation of pressure with depth, you can see a derivation here. But basically what we're getting at here is that the entire weight of the fluid, again, whether it's liquid or gas, has to be exerted on the bottom of the container. The walls are feeling pressure, but they're not supporting any of the weight. Again, weight is a force, right? Why is that? Well, the reason is that fluids, whether they're gases or liquids, can't exert shear forces. In other words, they can't try to push things sideways, right? They can only push against perpendicularly, I guess would be the word for it. And so all the weight of this fluid has to be on this area. Now, pressure is a different story. Pressure can be exerted and is exerted sideways into the walls of the container, even though the weight of the water is not. And the idea with this chapter is that the amount of pressure depends, well, it depends on three things, but most of the time, the only one that we have to think about is this height. Now, what we're saying is that if you're right here up near the top of the fluid, you're going to be feeling the least amount of pressure. Or another way to say it, this section of the wall feels the least amount of pressure. But as you go deeper in the fluid, now this section of wall has to support more pressure. Go deeper in the fluid, this section of wall has to support more pressure. And then at the very bottom, this section of wall has to exert the most pressure. Most of the time in our everyday lives, this doesn't really matter. For example, if you have a glass or a beaker, the bottom wall isn't going to be any thicker than the top of the wall because the pressure is not going to be enough to break the glass, right? Anything else to say about? I think that's about it. Height is the important thing to take away, though. Pressure varies with height. Now, there are two other factors that matter. One is density. You say, why don't we worry about the density? Well, the reason is that the density of most fluids, I should be careful how I say this, the density of most liquids is going to be the same at the top as it is at the bottom. Another way to say the same thing is that fluids are usually pretty incompressible. In fact, they're very incompressible. So, for example, the density of water at the surface of the ocean is pretty much the same as the density of water at the bottom of the Mariana Trench. The fact that one is 6 miles deeper than the other doesn't change the density because water is not very compressible. That's not true for gases. The density at the top of Earth's atmosphere is much, much less than the density at sea level, density of Earth's atmosphere at sea level, right? But that doesn't really affect container walls because there aren't very many situations where gases are going to exert much pressure, right? And so we don't really worry about that too much. Let's see, on the next slide, so what we're looking at here is a dam or a berm that's been set up to hold back some water. Okay, we know that the pressure, P, is going to increase as we go deeper and deeper and deeper. In this case, since we're holding back a lot of water and we're dealing with significant pressures, in this case, the base of the dam is much thicker than the top of the dam, right? Because the pressure down here is significantly more than up at the top of the dam. Now here's something that's very unintuitive. Does it matter how much water the dam is holding back? Think about that for a second. Does the thickness of the dam depend on how much water you're holding back? The answer is no. Now that's extreme, at least for me, that's extremely unintuitive. It seems to me that if I'm holding back just a little bit of water right here, I shouldn't need as thick of a dam as if I'm holding back a lake, right? That might extend back for several miles. What's going on? Why does the amount of water not matter? Well, the reason is the only thing that matters for pressure is height, right? So whether it's this thin column of water or whether it's 5 miles of lake, the only thing that matters is how deep is the water. That's what affects how thick you have to make the dam. Quantity of water has nothing to do with it. This is the last thing I'd like to draw your attention to in this slide. We're pointing out that the pressure is dependent on density. Well, okay, this liquid, this water is not compressible, and so the density is going to be the same at the top as it is at the bottom. It's going to depend on gravity, and what we do is we assume that the acceleration of gravity is going to be the same at the top of the water as it is at the bottom. Even if you're talking about things that are deep like oceans, that's a pretty good approximation. And so although these matter, they don't. We put them in the equation for calculations, but they're not things that change. Height is the thing we focus on because height is the thing that's going to change, right? If you look at this and you say, well, wait a minute, Cato, this is just what we were calling gauge pressure. Bam! That's exactly right. Yeah. This pressure is a gauge pressure. Now, technically, to get the whole thing, to get the total pressure, you would have to include the air pressure above the water plus the amount of pressure you're getting from the water at that particular depth or height, right? Here's a comment on solving math problems. You don't have to put, I know this is underwater, but you don't write H as negative. H is really considered a depth. So this H, even though it's underwater, is still a positive number. I can't think of anything else to say about that. One interesting thing, I forget if this is a homework question or not, but you could say, look, if I'm on top of the water, I'm feeling 1 atmosphere of pressure. How deep underwater do I have to go to double that so that I feel 2 atmospheres of pressure? And it turns out if you use this equation and you do the math for it and you solve for this height using the density of water, acceleration of gravity, and you just put in 1 ATM, right? It turns out that you can go 30 feet, technically it's about 33 feet. Well, no, it's about 30 feet, a little over 30 feet underwater before you get your 2nd atmosphere of pressure. 60 feet underwater would be 3 atmospheres of pressure. 90 feet underwater is 4 atmospheres of pressure, and so forth. Let's see. Yeah, this slide is designed to just get us thinking a little bit about atmospheric pressure. We've got a square meter of surface area here, and we say, well, what's the pressure due to the column of air above this? And again, all the air that's on the outside here just doesn't matter. All we have to think about is the air. You say, well, what if the wind is blowing? Well, that's fair, but any air that leaves this column is being replaced with brand new air that's entering the column, right? So it doesn't really matter what's happening in the atmosphere. Now, you could say that there's high pressure and low pressure, and over hours or days or weeks, that's true. Atmospheric pressure can change. But over a few minutes, unless you've got a tornado or hurricane or something, atmospheric pressure doesn't normally change that quickly, right? And if we assume a still atmosphere, then what we would say is the weight of this column of air works out to be about 100,000 newtons. The weight of 100,000 apples is slightly more, distributed over this 1 square meter. That brings up an interesting question. Does this thing go up indefinitely? And the answer is no, it goes up about 60 miles. Typically, people say that space starts at about 60 miles above the surface. Why? Well, the way space is defined in my understanding is it's the height at which an airplane can't fly fast enough to generate enough lift to keep itself up. Right? So let's think about that. Airplanes flying horizontally generate lift that keeps them from falling to the ground. But as you fly through thinner and thinner atmosphere, you get less and less lift. So space is defined as the altitude at which an airplane cannot fly fast enough. There's no speed at which that airplane can generate enough lift to keep itself from sinking or falling. And that's usually right around 60 miles. So this is how atmospheric pressure gets defined.